Howdy, welcome to another introductory video to Predicate Logic focusing on translations. This is 5.6 and 5.7 of the Suppes and Hill textbook. Unfortunately, the Suppes and Hill textbook is lacking on the issue of existential quantifiers, but we will remedy that as we go forward. This is unfortunately just one of the weaknesses of this textbook. But for now, let's concentrate on universal quantifiers, which is the subject matter of section 5.6 of the textbook. I should note, by the way, that predicate logic which was principally developed by Frege, in a way combines categorical logic with propositional logic. In categorical logic, we have something that is Aristotelian in spirit, although it may not be exactly identical to Aristotelian logic. Categorical logic, as is presented in most textbooks, is a little bit of a shallow version of what was developed in the Aristotelian scholastic tradition. But in any case, in categorical logic, you look at a proposition and you think about the terms contained within it. You think about the subject, you think about the predicate. But in propositional logic, you only think about the relationships between various sentences, where you don't think about what's within any given sentence. Now, predicate logic, in a way, combines categorical logic, or at least a version of categorical logic, with propositional logic. So you can think about the terms within a given sentence, you can think about the subject, you think about the predicate, but also you can think about various relationships such as the and, or the or the if and only if, and so on and so forth. Now, here's an example that comes from the textbook, or at least a version of this comes from the textbook. Think about the sentence we have, x is an even number. Now, a sentence like this is not true or false. But by replacing x with 4, we now have a true statement, because 4 indeed is an even number. Consider this. Here we have, for every x, x is an even number. Well, if we're going to say that the domain is every x imaginable, that's definitely false, because there are numbers that are odd, okay, like number 3. Now, in this last example, we have the universal quantifier for every. And other terminology that you may encounter would include for everything, or for everyone, or for all x, or all things, or any, and so on and so forth. Now, in general, x can refer to anything in the universe. However, we can restrict it. And oftentimes this is implicit based on the context. So if we're thinking about mathematics and we're talking about for every x, it's implicit in the context of that sentence that it's only talking about numbers. It's not talking about non-numbers. And this restriction we can call the domain of individuals or the domain of discourse. Probably the best way to learn this material is through examples. For every x, x is a material being. It's a good way to start. For every is a quantifier. It's quantifying something. It's quantifying x. And it's a universal quantifier. In predicate logic, we always symbolize this with an upside down a, and that just means for all, or for every. Immediately following a quantifier, such as a universal quantifier, we have our variable. It's a bound variable. In this case, it is x. Generally speaking, we use the reserved variables x, y, or z. So for every x, x is a material being. Material being is our predicate. How would we translate this into predicate logic? This way. For all x, x is a material being. And of course, material being is our predicate. It's a predicate about our variable x. X we call a bound variable because it's bounded by the universal quantifier. Our predicate m we can call a free variable. It has no quantifier at all. How about this? everything is true and good. Everything is a quantifier. There are two predicates, true and good. We also have a conjunction there. So we'll translate this as for all x, x is true and x is good. How about this? Nothing likes poisonous mushrooms. We have nothing. It's still universal in scope. That's important to recognize. It's still universal in scope. And our predicate is likes poisonous mushrooms. We have a negative universal statement. And this is how we would translate it. For all x, x likes poisonous mushrooms, but we are denying that, so we have the negation sign. So it's a universal statement, and the negation side is with the LX part. And it's important to note this because this statement here is not the same thing as not parentheses for all x, LX. Because this negation side is really denying this universal statement. So we would no longer have a universal statement. So this statement here and this statement here are very different. And if it doesn't make sense exactly why, you'll realize it soon enough as we continue on. All right, let's enter section 5.7, two standard forms. Let's consider sentences with two common nouns. For example, take the sentence, every man is an animal, where every is our universal quantifier, and we have man and animal. In fact, man is a common noun, and animal is a common noun. So it has two common nouns, and both of those terms we will treat as predicates, which may be a little bit confusing because we will also consider the subject of that sentence, namely man, as a predicate. In categorical logic, we never would consider man. The predicate, we would just say man is subject. But it does make sense to treat it as predicate in relationship to our bound variable x. So here's a translation, well, I should say kind of a intermediary step towards the symbolic notation. So we'll say for every x, if x is a man, then x is an animal. In other words, man is a predicate of x, and animal is a predicate of x, at least in terms of the antecedent location and the consequent location. So in the antecedent, we have man as a predicate of x. In the consequent, we have animal as a predicate of x. And if we get that into our predicate logic symbolism, we'll have for every x, if x is an m, then x is an a, where of course m stands for man, a stands for animal. So if we take this sentence here, put it into our notation, we get this. It's a conditional. I want to have a few notes here. So note 1, if we were dealing with propositional logic, we would only get this, m. Okay, that's the only way we can translate that sentence. So we could see already that predicate logic is much more sophisticated. Note 2, in predicate logic, we treat it as a molecular sentence, okay, because one atomic sentence can only handle one predicate. So our molecular sentence is this guy right here, okay, because we have two predicates. In the previous section, we had one predicate, but now we have two. Note 3, if we said for every x, x is a man and x is an animal, we have something that has a totally different meaning. That is to say, if we say for all x, m is an x and a is an x. So this statement here is totally different than this statement over here. Okay, so this new statement, for all x, x is m and x is a, it says everything is a man and an animal. It says everything is a man and an animal. Whereas the other statement, where we treat it as a conditional, we're saying if it is a man, then it is an animal. Indeed, we want to restrict animality to mankind. Okay, we don't want to say every single thing out there in the world is an animal. Also, as a technical note, we consider this statement for all x, if x is an m, then x is an a. It is a hypothetical in that it's not saying that in fact men exist. Okay, it's just saying if men exist, then men are animals. So it's hypothetical. This deals with the so-called existential import or export. But in any case, it's pretty straightforward. Together, let's do a couple of examples. Here's one from the textbook on 206. No man is immortal. First off, we have our universal quantifier, no. And we have two nouns, or two terms, or two so-called predicates. We have man, and we have immortal. It's a little bit confusing to think of man as a predicate, but we're thinking of it as a predicate of our bound variable x. So if we translate that, we can say the following. For all x, if x is an m, then x is not an I. So if we have a man, then we know he is not immortal. Note where the denial is located. So if x is an m, then x is not an I. How about this example? Not all philosophers are radical skeptics. We have our universal quantifier, all, but notice that this not is in front of that, and it's denying that universal quantifier. So we're going to have a negation right in front of our universal quantifier. As far as our terms or our predicates, we have philosophers and we have radical skeptics. So we translate that into predicate logic symbolism. We have not for all x, if x is a p, then x is an s. So notice where the negation is located. Moreover, if we consider the sentence, not all philosophers are radical skeptics, this would be equivalent to saying that some philosophers are not radical skeptics. At any rate, let's just consider it as it is given, namely, not all philosophers are radical skeptics. So we have the not, the negation in front, and we have if x is a p, then x is an s. Let's try to generalize some of this a little bit. So let's say we have the sentence, all A's are B's. So we have this sentence right here. How can we translate that? So all A's are B's. So we'll say, for all x, if x is an A, then x is a B. So that captures that sentence. What about no A's are B's? How should we write that? We'll say, for all x, if A is an x, then it is not the case that B is an x. So that symbolic notation captures that sentence. So these are two general forms dealing with our universal quantifier. Moreover, if we wanted to consider this right here in a more generalized form, I suppose we can say not all A's are B's. So from that, we can say not, parentheses, for all x, if A is an x, then B is an x. With that in mind, let's do some more translations. We have here all pines are evergreens. So we have two terms. So we have two predicates. So we'll have the universal quantifier all. So for all x, if x is a pine, then x is an evergreen. Number 9, every stream runs downhill. So for every x where x is a stream, then it runs downhill. Number 3, no man is an island. So for every x, if x is a man, then he is not an island. Number 7, no fifth grader is an infant. So for every x, if x is a fifth grader, then this person is not an infant. Number 10, no fairy tales are true histories. So for every x, if x is a fairy tale, then it is not a true history. The next sentence is only men are rational. Only means all. So for every x, if x is a man, then x is rational. Number 4 is all birds and fish are animals. Here we have to be careful because we might make a mistake. For example, we could not say for all x, if x is a bird and x is a fish, then x is an animal. That doesn't make sense. It's saying if x is both a bird and a fish, then it's an animal. So that's no good. However, we could change this conjunction into a disjunction. We're saying if x is a bird, then it's an animal. If it's a fish, then it's an animal. That makes sense. So we could say for all x, if x is a bird, or if x is a fish, then x is an animal. Alternatively, we could say something like for all x, if x is a bird, then x is an animal, and for all x, if x is a fish, then x is an animal. This also would work, but I think this version is preferable in terms of inferences and deductions. That will be more helpful than this statement in general. Number 7, not all men are intelligent. The not is denying the universal quantifier. So we'll say it is not the case that for all x, if x is a man, then x is intelligent. Number 5 is for all y minus 0 equals y. Before we conclude this video, let's think a little bit about particular statements. A particular statement will have a so-called existential quantifier. However, as I said, the Suppes and Hill textbook unfortunately doesn't address this explicitly, so we'll address it here and in the future videos as appropriate. In any case, we do know, of course, about universal quantifiers, and these deal with all or none statements. However, they don't affirm existence. We treat them as hypothetical. If I say all men are mortal, in predicate logic, I'm not thereby affirming the existence of men. I'm just saying if men exist, then they will have the attribute of mortality. On the other hand, existential quantifiers do affirm existence. For example, some men are mortal. If I say some men are mortal, I'm saying that there do indeed exist men. Likewise, if I have a so-called singular statement, such as Socrates is a man, I'm affirming his existence. Or I should say, in this case, I'm affirming that he has existed in the past. And we can think about this in the so-called square of opposition. If you know categorical logic, you've heard of the square of opposition. If you haven't, that's okay. But it's a good tool to use here. Now here I don't have a square, I have a rectangle, but it's hard to fit all this in. So we have all SRP, no SRP, some SRP, and some S are not P. We have 4 propositions here. And we can think about them on the square of opposition. For example, all SRP and some S are not P are logically contradictive propositions. If it is a case that all S are P, if that's true, it's impossible that some S are not P, or vice versa. That is to say, if it is true that some S are not P, it's impossible that all S are P. And likewise, no SRP and some SRP are logically contradictive. They can't both be true simultaneously. If one is true, the other one necessarily is false. And if one is false, the other one necessarily is true. In any case, let's think about predicate logic and how we can translate each of these. We already know all S are P. We can say for every X, if X is an S, then X is a P. For no SRP, we have for every X, if X is an S, then X is not a P. But how about some SRP? Here we will use the existential quantifier. And this is like a backwards E. Okay. So some X, for some X, X is S and X is P. In this case, we're not using a conditional. We're using the conjunction, the and. We're saying that there is an X that is S and it is P. So some S are P. And for some S are not P, we'll have the following. So for some X, S is an X and P is not an X. Again, we have the conjunction, the and. So for our universal propositions, we use a conditional. For our particular propositions, we use a conjunction. With the introduction of the existential quantifier, let's do 5 examples here. The first one is someone lied. There's only one predicate, namely lied. And someone is definitely a particular proposition. It's not a universal one. So we'll say for some X, X is an L. Example 2, if someone did not lie, the only difference is denying the predicate. So we'll say for some X, X is not L. For 3, we have some animals fly. We have 2 predicates, animals and fly. So we'll say for some X, X is an A and X is an F. That is to say, some animals fly. They are animals and they fly. So there's a conjunction. Example 4 is something is either an animal or flies. The difference here is this or, so we're going to have a disjunction. So for some X, X is an A or X is an F. For number 5, some people are selfish and others are charitable. Here we have people, selfish, and charitable as terms. So we got to be very careful here. So we'll say for some X, and because this is so big, I'll put this in brackets here. We can say that X is a P and X is an S, so that's in parentheses, or X is a P and X is a C, and that's in parentheses, and we close our brackets. So this is saying that some people are selfish, some people are charitable. We can also say this is equivalent to the following expression. For some X, X is a P and X is an S or X is a C. This is a more compact version. So X is definitely going to be a P, and it'll either be an S or a C. And if you know the law of distribution as a logical equivalency, this expression here and this expression here are in fact logically identical. The other thing to quickly point out, in case there's any confusion, is this AND statement. So I put a disjunction, right? I couldn't put a conjunction. That wouldn't make sense, because then it would say X is simultaneously selfish and charitable. But no, we have this distinction between those that are selfish and those that are charitable, so we must have a disjunction. And that concludes this video. Thank you so much for watching. If it has been somewhat helpful, please consider giving this video a like. I would really appreciate it. And up next is part of the Chapter 5 review test. I'll see you soon.